All right, so let's try this again. So let's try to find the potential function of f of xy equals 2xy minus secant squared x, comma, x squared plus 2y. So first off, let's check and make sure that it is actually a conservative vector field. So we're going to take the partial derivative of the first component, which is 2xy minus secant squared x. That's the x component, so we're going to do the partial with respect to y. So the partial with respect to y, the first piece comes to 2x, and then the secant squared x will just be 0. So then we're going to do the partial of the second component, which is x squared plus 2y. That's the y component, so we're going to do the partial with respect to x. So then the x squared becomes 2x, and the 2y goes to 0. So these are equal. So this is conservative. So now let's find that potential function. So let's kind of follow the same steps that we did last time. And this time I've kind of written out a little scaffold outline for the steps. So the first thing we're going to do is we're going to start with one of the components, say f sub x, which is like m. So this is like the integral of m, and we're going to take it dx to try and go backwards to look for f. So we're going to then look at integrating. We've got 2xy minus secant squared x, and we're doing this dx, where this is a multivariable function. So the 2xy, we'll treat y as constant, so we'll increase the power of x to x squared, divide by 2, which cancels this 2, and keep the y. The integral of secant squared, hopefully we can remember, is tangent. So then we'd have minus tangent x. But then remember, we need that plus a constant function. And since this was a dx integral, this is going to be plus a constant function of y. So we have some extra piece of y that we're not sure what it is yet. Now what we want to do is we need to then look for f sub y of xy using step 1. So using this is our f of xy. We're going to now look for the partial derivative of that with respect to y. So when I take the partial derivative with respect to y of x squared y minus tangent of x plus c of y, what we're going to get, the first piece, we keep the x squared, and then the derivative of y goes away, so we're left with x squared. We're left with the minus tan x is just going to go to 0. And then we're left with the derivative, which this time I'll say write it like this, the derivative with respect to y of c of y. Last time I wrote it as c prime. Same thing. So the same thing either way. Okay. Well, remember that this really should be the same as my n component up here. So let's solve for that c prime of y. So what we really should have is this should equal n. So let's take x squared plus, I'll write it as c prime of y should be equal to x squared plus 2y. What we have is that constant function of y can be pieces from this n component. So canceling out the common things, we cancel an x squared, we would see that c prime of y should be 2y. So the derivative with respect to y of just that constant c function of y should be 2y. So now let's try and find c. So c of y, well, let's go backwards again. To get c from the derivative, we'll do the integral. So c of c prime dy will be the integral of 2y dy. So y is going to go up to y squared, divide by that new power. So we really end up with y squared. So 2y squared divided by 2 is just y squared, and then this one gets a plus, a scalar constant, because we're just integrating a single variable function, so just plus a scalar. So now we've got that c of y is y squared plus c. So what we can do now is plug that back in over here. So what we have then is f of xy. Over here we had x squared y minus tangent of x. And then we have plus the constant function of y, which does now include a y component. We've got strictly y squared plus c. Now you might be thinking about, can I check that this is right? Well, yeah, it's fairly easy to check if it's right because we just need to do the derivatives. So if we want to check this, just do those first partial derivatives. So the partial derivative with respect to x of f, well, we'll have bring down the 2, so we'll have 2xy minus the derivative of tangent, which is secant squared x. And then plus y squared is 0 when we take the derivative with respect to x, and the constant, the scalar constant c, is 0 with respect to x. And we can double check, is this equal to my m component? Yes, it is. So this equals m, which is good. And then take the partial with respect to y of f. So x squared y just becomes x squared. Negative tangent x goes to 0 with respect to y. And then plus y squared would be plus 2y. And the constant, the scalar constant c, would have a derivative of 0. So then we're checking x squared plus 2y, which is indeed my n component. So we've confirmed that this is correct. So that we have the gradient of f is indeed my vector value function, capital F, which is excellent. If you want to, if it seems easier, there's no particular reason that we chose to use the f sub x component first. You could use the f sub y component first, and then you would just have to accordingly adjust what you do after that, right? Then you'd be kind of having like a constant function of, if you had started with the f sub y function, when you integrate with respect to y, then you'd have a constant function with respect to x. So then we would be comparing that to the x component and looking for, well, what does that c of x look like, and so on and so forth. So you could just flip-flop all of the roles if it seems easier for some reason. But it doesn't make a difference which way you do it. You just have to be consistent.